All right, thanks. Thanks, John. I also want to, especially commend Rotham and Disha. They let me put the laptop here because I wanted to show a demo, and I want to say, I'm building ZK, useful ZK, but the way they just arranged this and got it to work, I'm amazed. I just want to say that one of the hardest problems is sometimes just, connecting your laptop to the screen. So special thanks to them. This is, I think, the third time I'm presenting the Ligero zero-knowledge systems in the ZK proof. I presented it first in DC, last year in Berlin, and now over here. And the YouTube videos actually serve as an amazing snapshot of how the system has evolved. Also, this is one of the few venues I love presenting because I can do a demo and show about the system, but at the same time talk super technical stuff, right? And the audience is very encouraging to see both of these things. I do know I'm standing in the way between you and your dinner activities. So let me give you the bad news first. The answer to compile or precompile will come in the last slide. So, all right. So just some high-level motivation of what we are trying to do at Ligero. I want to say today privacy comes with a lot of trade-offs. Often, you want to use privacy chains like Aztec, Zcash, you have to let go of compliance. Privacy comes with cost. Modern ZK systems that are trying to scale to very large applications demand very large hardware or expensive GPUs. Some of the ones that are private are a little less usable because they use what I call non-standard tool chains. You got to learn a new language. There are a specific set of developers that you will need to develop applications in this. And finally, many of the real-world solutions often use some centralized entity for trust. So privacy comes with trade-offs. What's our vision is to build useful and usable privacy tools with zero infrastructure cost. Now, that sounds like a really marketing gimmick, so let me refine this statement a little bit. Where we are starting is useful and usable zero knowledge with zero additional infrastructure cost. And for people who have seen zero knowledge, this is in line with the philosophy that zero knowledge is not really zero knowledge, it's zero additional knowledge. So in my mind, I'm again being very biased in this presentation. So useful ZK, I want to say, is about how easy is it to code applications in this. At the beginning, it was about feasibility. You had to do carp reductions. These were not going to be implementable. But then it got better. People started developing zero knowledge for arithmetizations in Boolean and arithmetic circuits. But then blockchains came, and this kind of supercharged, as Dan eloquently put in his presentation, the development of zero knowledge. And many languages came to make useful zero knowledge systems. But it still required learning these new languages. Today, we now have many ZK systems that are VM-based. What this really enables is that you don't need to learn a new language. You can code in Rust or C++ and compile it down to these VMs and employ a ZKVM. Usable in my mind, just when it comes to ZK, ZKVM, again, enables a lot of developers to use your system. I want to say zero additional hardware in that you can do it on your device. This is what I mean by zero additional cost. It'll be great if you can do the zero knowledge on your cell phone, on your laptop. A portable implementation, I shouldn't have to buy a 4090 or a 5090 to run my system. And finally, I don't want pain, I don't want caution, I want my system to be ZK. So modern ZK falls short, and take whatever I'm saying with a grain of salt because people are trying to improve it. ZK snarks require huge memory. Okay, the ones like Groth16, etc. You need a huge proving key. Start-based ZK don't run client-side, and I caveat it with yet because they are working on it. And most ZKs are built only for verifiability. I mean, as you saw in Uri's talk, how hard it is to get ZK into some of these systems. And the ones that offer privacy, like the ones like Aztec, etc., or even Circom, they require specialized tool chains. They are not ZKVMs. As is customary, I don't know, in blockchain, there's usually a Vitalik quote that reflects the situation, where he says that ZKVMs haven't reached privacy applications because these ones don't run client-side yet. So what we are trying to do is we want to challenge this. We want to be able to develop things that run from a browser, from your device. And as I want to say, Sophia mentioned about asking people to develop more of this ZK, this is what we are really trying to power using our ZK. So with this, I want to show our platform. I want to do a demo, and then I'll come back. Okay, so here is sort of, I'll give you links at the end. We have a platform. It's now open for the public. This is just a speed test that we have where you can see how fast your device can run our system. It really, this kilohertz, you want to interpret it as number of constraints per second. So this is saying about 4 million constraints per second. And to get some perspective, you can imagine that I'm doing 20,000 Poseidon hashes per second on this browser. But granted, I have to caveat this. I recently bought this laptop like a month back. It's M4 Max. It's like the highest end of the MacBook, just to see its performance. But even on an M1 MacBook, it is pretty fast. Now, here is our platform, which is open. I'll again put the link at the end. You can sign in with your Google credentials. You can build ZK applications from the browser. You don't have to go do GitHub clone, find dependencies, nothing. You go to the browser and you can develop a zero-knowledge application. You can deploy it and make it available for people. So I'm going to show one of these deployed instances. It's just doing a very simple computation, edit distance. Okay, it's been deployed to the marketplace, and I can prove it straight from the browser. Now, I can also verify this on the browser. I can send the proof. You can test this out in the platform, on your laptop or on your phone. What I want to show you is once you log in, you can also create new projects. These are some of mine. I'll pick the edit distance example that I had chosen. You write the edit distance in C, C++. You compile it. So ours is a ZKVM that is based on WebAssembly. So what happened when I hit compile is it went to, this is the only part that left my laptop. It went to a backend server, compiled it to WebAssembly, and I got it back. If you don't like it, you can locally download mscripten, which is a standard LLVM compiler, compile your program to WebAssembly, and use it. And then you can go to run. You can prove it. Now, you can also deploy it. It goes to the marketplace. And in the marketplace, you can also download the files that you need to prove it. You don't need to use our marketplace to run the prover. And just in the interest of time, let me show you this, where like this edit distance example, these are the files that get downloaded. There's a prover WebAssembly, a verifier, and an application WASM file. I want to say that, in fact, in all of this, the JavaScript file and the application WebAssembly are the ones that change. The prover and verifier WASM does not change when you go from across applications. And you can see the sizes of these things if you want to put on any device. It's like a few megabytes compared to, imagine, Groth 16, which will require a gigabyte of proving key. I also wanted to do a second demo. I couldn't do it, but I still feel like I want to talk about this thing that I did. So I wanted to do this Battleship peer-to-peer game with zero knowledge. I know I'm revealing my age. Maybe half of you haven't played Battleship. It's like this old board game where you play ships and like you hide your board and like try to hit the other person's ship. This is a clean example of where you could use zero knowledge for peer-to-peer games. I hash my board, give it to you. Every time you call out a coordinate, I reveal the coordinate, and I prove with respect to the hash whether it was a hit or a miss. What I did, I went to ChatGPT. I said, hey, build me a web app for Battleship. I gave a few constraints. It built it. In one call, it built it. It was a web server app. Like I could open 2 browsers, I could play ships, and I could play it. It was a React code that it generated, and I could run it. And then I was like, okay, let me go to my platform and then write the predicate for the Battleship, for proving this Battleship. But then I thought, let me do one step better. Let ChatGPT do this predicate for me. So I went to ChatGPT again, and I said, hey, like, can you build this predicate in C, C++ for me to do it? it did it. I put it over here. I had to still do a little more plumbing because even though we are C, C++, there are some kind of directives I have to use for assertions like, something is true, false. I have to put some of them. But then I compiled, and I could run. So now the predicate is running. What I didn't do is take this zero-knowledge system and plug it into the web app that I had. And I'm sure that any of the hackers here would be able to put this into the thing. I should say that I stopped coding since I finished my undergrad. So now I'm using only ChatGPT to build my code. Anyways, with this, I'd encourage all of you to try this platform. You can code directly from the browser. You can deploy it in a marketplace. You can show it to your mom, your grandmother, grandfather. Hey, I've developed a zero-knowledge application. And even if you don't develop it, you can go to the marketplace, hit prove, and you have proved a zero-knowledge proof on your device. All right, so with that, I'm going to go back to my slides. And I want to say that kind of concludes the demo part of the presentation. So if you don't want to hear the technical part, thanks. If you don't want to hear the technical part, I wouldn't hold it on to you if you leave for your dinner. So what I want to do in the rest of this presentation is to talk a little bit. I've not presented the Ligero system like technically anywhere. And I thought I'll use this place to talk about the Ligero system and why we are able to run it on a browser. And one of the crucial things I want to say is that we are memory efficient. The prover for the Ligero system is needs only memory proportional to the memory required by the underlying WebAssembly program running natively, roughly proportional to that. And I call this the Ligero zero knowledge. I also want to say, John was saying for new. I want to say that the new version, the memory efficient version, is still our old Ligero zero knowledge system that we published in 2017. The only change we did is we made it memory efficient. So this new system, we call it Ligatron, is still the Ligero zero knowledge. It inherits the same hash-based and proof length, etc. The main difference is now the prover can fit in a small device. All right, so just a little bit of benchmarks before I go into the technical details. This is some of the Stark's benchmark. I think this is a year back. Again, I just copied this from one of their from news articles. The Stone Prover, which was the first version of Stark, they were able to do the Poseidon hash function on a 252-bit prime, about 530 per second, on a quad-core Intel i7. The new version, they did two things. They reduced the prime from 252 to 31, and they moved from Poseidon to Poseidon 2. And they were able to get a lot more bandwidth by doing that to get like about 500,000 hashes per second. What you saw on the browser that I ran over here, actually the peak was about, I can do 27,000 hashes per second on a 254-bit prime. And I want to say, we can also go into a small prime, like we just need an FFT that works. We need to read Solomon codes over the prime, and that's all we need. We can also go to like the Circle Stark prime if we want to, but we chose to remain in the 254-bit regime because, again, it's easy to do EDDSA, etc. on this prime, as well as do certain recursive composition to verify these proofs on chain. So we're able to get good throughput on this, so we still don't have an incentive to switch to a small prime because our performance is good. Here's a little more, again, high-level comparison. CirCom, as I said, I didn't give the runtimes. The runtimes on a browser are pretty slow. But I think the bottleneck more is about the proving key sitting on your mobile phone, etc., if you wanted to use it. Noir, which is, again, an up-and-coming client-side proving by Aztec, they have really extensive support for all kinds of primitives. We were able to benchmark, again, this was about a month back. They're around like the 40, 50 kilohertz, and on an M1 MacBook, we can go from 250 to 1 megahertz depending on the complexity of the circuit, and on M4, of course, much better. All right, so Ligatron, which is the memory efficient version of Ligero, I want to say it's a memory-efficient hash-based system. So in all aspects, in terms of features, etc., it's like a Stark. We don't need any public key primitives, and we just use Merkle trees for this hash function. It's ZK by default, and I can tell you a little more about why it is ZK by default. We are a ZKVM based on WebAssembly, and the way we accelerate is using WebGPU, and we made a conscious decision not to use CUDA because then it's not going to run on all devices if we wanted it to run on cell phones. So we do take a performance hit, but I don't think it's significant. Like, I don't think WebGPU to CUDA, I would guess it's within 2 to 3x when it comes to the kind of things that we are trying to prove. So what's the secret ingredient? It's hash-based. We use code interleaving that helps us with parallelization, helps us with memory efficiency, and also that the Ligetron system can take both the witness and constraints in a streaming fashion. It can process this in a streaming fashion. But I really want to say there is no secret ingredient, and that's just my older daughter is into Kung Fu Panda, so I wanted to put that over there. What I want to say is that the Ligero zero-knowledge system is based on MPC in the head. If you can look at the MPC and say, can I have these properties, then those properties translate into zero knowledge. Like memory efficiency, parallelism, code interleaving, everything you can see it. If you see it from the MPC in the head perspective, you'll see that, yeah, it just follows.
Muthu?
So yes?
So for MPC in the head, you actually presented that, I think, in Berkeley.
Yeah.
And it was a beautiful presentation that went deep into the details. If people want to learn about that, that also hasn't changed, right? That also hasn't changed since 20...
That hasn't changed, yeah. And I'm actually going to do it again, so you don't need to see the old video. Okay. You can see the one I'm going to present in the next few slides. All right. Rest of the talk, I want to talk a little bit about why memory efficiency is hard, let's say, for example, for Stark systems. And then I want to say that one of the things with the Ligero system is that the verification is not succinct. And you can argue why it is inherent, but also there is a way that people get around achieving succinctness by using what is called like a pre-processing snark. So I want to present how to make Ligero a pre-processing snark. And finally, answer the question, hopefully, about compile versus precompile. All right. I want to say that, again, I'm very biased. I'm focusing just on hash-based systems and constructions that are black box in the hash-based system. And I think it helps to understand this. I mean, not that recursive composition and sharding, etc., is not good. I think understanding the complexity of doing this under a restricted setting of hash-based and black box tells you how much you can extract before resorting to recursive composition. All right, so why is memory efficiency hard? The short answer is that there is a time-space trade-off for error-correcting codes. And I want to try to convince this to you on a very high level that why is there a time-space trade-off for error-correcting codes? So I need to define a model under which I want to say this is hard. And this could look like a restrictive model, but I think it's good enough to capture the intuition of why it is hard. So I'm going to assume my encoding algorithm has linear access to the input. And then it has some work tape, which it has RAM access. And then there is an output tape, again, that it linearly outputs things onto this chain. So how would it look like? So the encoding algorithm would start reading up to some point, and then it'll start outputting onto the the encoding, read some more, then output some more, and done. Right? So this is how I view the encoding algorithm. I push the RAM, the work tape behind the scenes. But you can imagine that at every step of the way, it could do things with its internal work tape. Now, here's the first thing I'm going to say. Just by counting arguments, you can show that there is let's say that delta is the distance you want in your error-correcting code. Now, you can identify a chunk of size delta n over 2, where n is the length of the message, that could have influenced at most delta m over 2 of the output. Now, the idea being here is that I'm going to show you that there would be if the space that you have in your memory is not big enough, there would be two messages that would affect only this chunk. That would be a contradiction because you want the distance to be at least delta m. Okay? Now, the first I'm just arguing by accounting, I can say that when my work tape starts reading there is a point I can identify a chunk where I start at the beginning of the chunk there, and my output head is over here. And when I finish that chunk, my output head is over there. I can identify such a, such two blocks just by a counting argument. Now, I want to say that the number of possible messages that I'm going to keep everything else fixed, and I'm only going to change this middle part. And the number of such messages, if I'm using some field, it's like f to the delta n over 2. That many messages, I can change just the, that's a yellow, right? Like I'm colorblind, but the highlighting is yellow. Okay, good. Now, I want to say, but what I've ignored in all this discussion is there is RAM, right? Like, so I have to incorporate the fact that now there are so many messages there that influences only this, but if I want the rest of the encoding to be identical, when the head reaches this point, I need the work tape to be identical configuration. If that is, if I can achieve that, then beyond that, when I process the rest of the input, these things would be identical. Okay, so all I have to do is I have to remove the entropy of the space. So the number of messages with the same work tape at the end when it finishes reading that chunk would be this. Now, if this is greater than 1, I have arrived at a contradiction. Okay, because I have two messages that influenced only a small portion, and this violates the distance argument for the error correcting code. And so this gives s greater than delta n over 2. I've made many simplifying assumptions, one of which is I only took one pass on the input. What if I took r passes? So in a paper, we proved this, that for an r pass algorithm, this s needs to be greater than delta n over 4r. But the net result, really, what it is saying is that if you want to do FFTs, which is like quasi-linear n log n in your input message length, then your space needs to be omega n. Okay, maybe modulo some logins, but you need that much space. So imagine that in Starks, where all of these are like in a huge, and there is no recursive composition, so you will have to put all these values in a long code. You need that much space. And if you actually saw the stone prover, etc., the initial implementations used a terabyte of RAM. And even I think the recent ones uses like, I think, I want to say around 500 gigabytes, but my information again is probably a year old. Our system actually doesn't need that. We have to pay, there is some trade-off in getting memory efficiency, but we get around this lower bound by trading off in proof length. And I'll tell a little more about it as I describe the system. Okay, so the next, I want to talk about the Ligero system. I'll tell you high level why it is memory efficient, and then I want to talk about how we can get succinct verification. Okay, I also need to explain why we need succinct verification. I'll do that while I describe the Ligero system, and then I'll show how we can edit it. All right, so here is the Ligero zero-knowledge system. I'm close to explaining or describing the entire system. So first, you take, let's just simplify our world. No ZKVM circuits. I have inputs. I evaluate it. I get wire values. I take all the input and wire values and I arrange it in a matrix. Okay. How you arrange it? There is some. I need to tell you how there are some minor things in how you arrange it. But the flexibility you have is in choosing the dimension of the matrix. It should just have the capacity to have all the wires, but you can choose rectangle, thin, fat, etc. If you want optimum proof length, you want it roughly square root the number of values you're trying to put in. The first step, the prover constructs this matrix and then encodes it row by row. We're going to use Reed-Solomon codes, nothing more than that. The standard Reed-Solomon codes, pick any field in which this works. You can encode these wire values. Imagine each row, I'm going to encode it. For people in the cryptography space, what I'm doing here is packed secret sharing. Okay, and for people in the coding, I'm doing Reed-Solomon codes. Now, first step, we're going to build the Ligero system can also be viewed as a ZK IOP. So I'm going to construct a proof oracle, which contains the columns of this encoded witness. Okay? And the first step in the proof is the prover gives a commitment, which is really the Merkle root of this Merkle tree. And next, there is one challenge response where the verifier is going to check. There's going to be a proximity check. We learned all about proximity gaps, etc. yesterday. There's going to be a check to check the addition gates and a check for the multiplication gates, and then finally queries. In the IOP model, I would query directly, but when you realize it as a protocol, you ask the prover to give you with Merkle decommitments. This is the protocol. I'm going to explain these 3 checks next. One thing I want to mention in passing is that computing this encoding is memory efficient. Now, how much space do you need? Is that if the witness is streaming, which usually when you are evaluating a circuit, your witness can be streamed. Now, which means that the elements of my matrix can be generated row by row, the actual wire values. As and when a row is being generated, I can encode it. And remember that I'm hashing it. So as and when I encode it, I can also accumulate the hash. So the space I need is really the width of this matrix. Okay, and usually that's large enough. Like this, it'll fit within, I'd say, 100 megabytes a row of this. Even if you do very large width, it's not going to take too much space. All right. Another point I want to say that you want to pay attention while I'm doing these checks is a key property. In each of these checks, the prover is going to compute some kind of aggregate on the encoded witness. Okay? For example, one of these is the proximity check, which I'm going to talk next, is a random linear combination of the rows of the encoded witness. Now, I want to say that whatever aggregate the prover is computing, it will be a row operation, a matrix row operation. And this is going to be important because this will allow the verifier to spot check what the prover did with respect to the aggregate. If they are all row operations, then the verifier can repeat those on some select columns that it will query. So we're going to make sure that all these checks can be implemented using row operations. Okay, so here are the checks. The proximity check is easy. I'm going to denote the encoded witness, the ith row as VI. The verifier in this phase of checking is going to give some randomness. The prover gives a random linear combination. And the verifier is going to check if Q is a valid encoding. The reason you're doing the proximity test is to make sure that the prover encoded some set of values. It's sort of you want to get binding on the witness value. Now, just by checking that Q is a valid code word and later doing a spot check, you can guarantee that with high probability, there is some witness that is binding. And there's like a long line of works we had proved, and since we proved the soundness, this is improved to really a very tight analysis by Ben Sisson et al. Now, the multiplication check. Now, here is the part I said, I need my witness values arranged in a certain way. And really the way I'm going to arrange it is where I'm going to think of it as 3 rows at a time, which are going to capture all the multiplication gates. And I want it so that the value here times the value here should be the value here. I just want it in line. Okay? Now, this is easy. As I'm processing the circuit, I get multiplication gates. I just place it in my matrix this way so that they are aligned vertically on these columns, grouped 3 rows at a time. So in essence, this is the encoded witness. But if I looked at the real witness, if I multiplied these 2 rows at a time, I will get the value in the 3rd row. So that's how I arrange the wire values. And I'll also tell you that I only care about multiplication gates because the addition gates will not cause any witness values for us. So if I assume that my witness values has this configuration, now to prove that the prover did the multiplication gates correctly, the verifier is going to give some randomness, and the prover is going to compute this random linear combination of VI pointwise times VI plus 1 minus VI plus 2. Okay? Now, we're going to leverage a property of these Reed-Solomon codes that they are multiplicative, which means that you can do one multiplication, or you can do more, but we need just one multiplication is still homomorphic. And let me explain what this is in a minute. But if VI plus 2 indeed encodes the product of the values in VI and VI plus 1, then what's inside the bracket, when I decode it, it should be all zeros. Okay? Because I have aligned it in a way that they are the products. If the prover did it correctly, they should all be zeros. So all that the verifier has to check here is if Q encodes all zeros, this also can be spot check. okay? Because they are row operations. If you can see what I've done here, they are row operations. So when the verifier queries a few columns, it can check if Q was computed correctly on the selected columns. The soundness of this is 1 over the field size. I want to quickly tell you what's going on, what I told you about this homomorphic or multiplication property. If I have an encoding of, think of this as the wire values ABC, that's the encoding. I have a second set of wire values, that's the encoding. Now I multiply the encoding and then I decode, I'm going to get point-wise product of these things. And these codes are also additively homomorphic, so when I subtract it with Vi plus 2, that's why I should get all zeros if the multiplication gate was performed correctly by the prover. Okay? We're just using the fact that the Reed-Solomon codes are multiplicative over here. The addition check, this is really, I want to say, yes? No, there won't be a degree over F. Yes, I am. I have to. I have to do, the length of the encoding must be at least twice the degree, yes. Standard BGW, yeah. Okay, so the addition. Here what I'm going to say is that I have my wire values. I can wrap all the entire linear constraints as a single matrix A and a vector B, and I'm going to say that A times W equals B. This will, I'd be able to capture all the affine conditions or linear conditions via this constraint matrix A and vector B. I need to prove, or the prover needs to prove, that what it encoded here satisfies A times W equals B. Okay? What the verifier really is going to do, again, is a random linear check of this, is given a random vector R, it's going to check RAW is R transpose B. Okay? This is what it's going to check. Now to check this, the prover needs to give and prove RA times W. Because this is, the verifier will just take this and check if it's R transpose B. But how can it give RA times W and prove that this is correct? And the way it's going to do that is, you should think of this, R transpose A is a vector, W is a vector, and it's really an inner product between R transpose A and W. So the prover is going to take R transpose A, which is of the same length as W, arrange it in the matrix the same way W was arranged, exactly the same locations, if you think about it, indices to locations, and encode it the same way it was done. The prover is doing all of this in her head, and then let's say that Vi and Si are the ith rows here. The prover is going to give pointwise product of this Si and Vi and aggregate it. Now what I'm going to tell you is that, remember what happens with the pointwise product. We know that this is multiplication. Now Si is encoding the elements of R transpose A. And when I multiply it pointwise, I'm really computing these partial products of the inner product. Right? So each element here is getting multiplied with the witness, and then when I sum it up, each entry is a partial sum of the inner product. And when I get the Q and decode it, and I sum the values that it decodes to, I get the inner product of R transpose A and W. Okay? So again, it's just using sort of this multiplicative property of the code. Now, how is the verifier? There's one thing I need to mention here. How are you going to spot check this, the verifier? Because this R transpose A and encoding was done in prover's head. The verifier does not have access to it. So when it spot checks, it needs the entries of Si to spot check. So I want to say this is the part that causes Ligero to be not succinct. Because to get the columns of, let's say that those are the columns that it opens on Vi, on the encoded witness, the verifier needs the same columns in the encoding of R transpose A to recompute this this pointwise product of Si times Vi on those columns. In the Ligero system, in the original work, and even now, it recomputes, it does the computation. It does exactly this computation that the prover does. And that's big, that's the size of the circuit. This is why the verification is not succinct. All right, so looping back, this is our system. You commit, you do these checks, you do these queries. This is the Ligero zero-knowledge system. In fact, the implementation you saw is this. The only main difference is that it was memory efficient. The part that maybe just one point over here is that The multiplication you can see again, if my witness was streaming, it's again memory efficient. To see that this is also on the prover side memory efficient, I want to say that R transpose A can be streamed. Okay? As I read the circuit and I know what it is, I can generate these constraints, and I leverage the fact that constraints are local on this witness. Okay? This is something that I make assumption about the circuit, but it's not really an assumption. These, like, you know, when I do some comparison, it only is about values within that range, for example. So if you buy that R transpose A can be streamed, the prover can compute this aggregate SI times VI also using in a memory efficient way. This is how we get memory efficiency. What I am completely pushing under the rug is all the engineering and compiling effort that went into getting this done. Okay, so this is the system. The final point I want to make about the system and memory efficiency is that we have to go through the witness 3 times. First, to generate the commitment. The next time to answer all the tests, but you can do this in parallel. All the checks can be, the aggregates can be computed in parallel. So we need to recompute the witness from the start. And third, the queries. Okay? Because at no point of time, the entire encoded witness can be kept in memory. Okay? Because this is what we are trying to avoid. So we have to do this 3 times. And what you saw in the implementation on the browser, it goes 3 times. So one thing you can take away is if you give more memory, it'll be 3x faster. So every check, again, this was the key insight. Every check was a row operation, and I can check it column-wise with the spot checks. And the second part is that verification is not succinct because the verifier needs to recompute the encoding for the linear check of R transpose A. Now, I'm going to fix this. All right. So I'm going to just go ahead and tell you how we are going to do this. The idea is we're going to have the prover give this to me. Okay? So the verifier gives R, and I'm going to ask the prover to take this encoding of R transpose A and commit it to me using a Merkle tree just the way the witness was done. Okay? And now I'm going to have, this encoding, again, I need to check proximity test on the encoding of R transpose A. I also, when I do the queries, I have to reveal the same columns on both these commitments. Now this enables the verification to be succinct because the verifier no longer has to compute the encoding of R transpose A. The prover is giving this to me. Okay? But I'm missing one big thing here. Why do we trust the prover to give the right R transpose A? So that's the problem. Okay? I don't know that the prover gave me the right. But barring that one thing, the verification became super succinct, actually super parallel as well to do this. Okay. Here is where we're going to do pre-processing. Make this a pre-process. There's going to be a pre-processing step where I pre-process. I'm going to commit A, and then I'm going to do this. For people who have seen Spartan, this is kind of inspired from Spartan. Okay, so what's the idea? In a pre-processing step, you're going to sparse commit A. You don't want to commit A. A is really a sparse matrix, like it's only telling these constraints, so you want to do it in like sort of index form, Aij, I, j. And in the proof system, I'm going to make the verifier get a fingerprint or a MAC of R transpose A. Okay? What is a fingerprint here? It's very simple. You take R transpose A, you multiply by a vector S, I get this value alpha, I call this the fingerprint of the A matrix. Now, the verifier is going to check if it's going to get the same fingerprint from the sparse commitment A. So we're going to ask the prover, in addition to giving the usual Ligero proof, to give a second proof that alpha equals R transpose AS, where with respect to the commitment that was done in the pre-processing. Okay? This is how we make pre-processing smart. There are many details that I'm hiding under the rug. The point I want to make is that maybe the second proof looks like a chicken and egg problem, because I wanted it succinct. What if this one is not succinct? And I want to say this computation is like really very uniform. If I take R to be like powers of like a number, if it's like good randomness, this second computation, even with a sparse commitment, is a highly uniform computation. And actually, you can even use Ligero as the second proof, because Ligero is succinct on like sort of a batch setting or a highly uniform computation. So we can use any other system, like Spartan even, but and another point is that the second proof doesn't have to be ZK. It's enough to be a snark. I'm telling something about a public matrix A, and R and S values are also something that the verifier knows. What helps us in this has not been implemented, but if we did implement it, we wouldn't implement the second proof on the browser. It can be done on a backend server just to speed things up. All right, so verifier does not need to compute R transpose A. This makes it succinct. And the second proof, we need to use some other system that helps us do this. You can also use the Ligero system. 5 minutes, great, awesome. So this is, this concludes how we make Ligero a pre-processing snark. I mean, this has been a long time coming because this is almost a common criticism of the verification of the Ligero system. But this is like, we are implementing this soon. We should get some benchmarks on how expensive this is. The last part, which I hope I can do it in 5 minutes, is to talk about little bit about the overhead of VMs. And I want to coin this thing, again, it's not well defined, as sort of the mux overhead of VMs. And really, when I come to succinct verification, pre-processing is one way. But another way of getting succinct verification is by making your verification circuit very universal or like very uniform. And VMs actually take this approach. You imagine a CPU circuit that goes instruction by instruction, and I have a state of registers, and I prove from state transition to state transition it was done correctly, and the state transition is a uniform computation that you do. Okay, this is again, I'm pushing a lot of details on a very high level. But what I want to define the mux overhead here is the size of the CPU circuit by the size of any instruction or even the smallest instruction. Really, the point I'm making is that you're paying the price of the CPU circuit for every instruction, no matter what size it is. Now, a naive way of doing the CPU is just a big OR of all these gates. That's going to be huge. You will imagine then this overhead would literally be the number of instructions or more. You can use universal circuits. There are people who work like in theory that how to like take a whole bunch of circuits and sort of unify them. They're not yet, in my understanding, practical to make this universal. But there's also this more recent work of lookup singularity, Jolt, etc., where I want to say they still have a mux overhead. And the point here is that they make all instructions as a lookup, but they still have to unify all these lookups into like one verification circuit. They might look up into like a table in a unified way, but how they put together will still be different, and you need to pay some price of making it universal. Just imagine if you've seen a lookup for doing an XOR function is usually just concatenation of lookups, but multiplication is far more complicated. But your circuit should not let you distinguish between doing a lookup of an XOR and a multiplication. And this is an overhead there. So just a question here is, can we pay exactly the number of constraints needed by this instruction? And I want to say the precompile approach actually tries to alleviate the situation by saying there are some things that are done often. SHA, ECDSA, or certain primitives. Let me hand draw certain circuits and put them together into the system. But this is, you have to redesign now for every component. Now, we have a work where we can show that you can pay exactly this overhead plus some additional overhead of this. And the additional overhead is really one time running through the program. Okay? Now that seems a lot, but I want to say that typically when we think of a program, there could be for loop functions that are called many times. But independent of how many times they are read in an execution, the prover has to pay the price of doing it once. Okay? Now, I don't know if I have time, but I'm going to I'll spend a minute. If you don't get it, come and get me later. I want to say that I'm going to view a program as a collection of primitive blocks. What's a primitive block? Is something from which you don't jump from inside. Imagine a for loop where there are no exits, etc. Like I just execute it in sequence. I can view the whole control flow graph as these primitive blocks, and all I can do is at the end of a block jump to some arbitrary block. Okay? And I want to say that you have to pay once per blocks of the entire WebAssembly, but then after that, you only pay exactly the number of constraints in the execution. Okay, and roughly, again, this is really a 20,000-foot view of our solution. The idea is to extend this MAC that I was telling you with for this situation. And I know I'm going to rush through this, but I'm going to try it anyways. Take your primitive blocks, call them 1, 2, 3, Each of them define like a linear constraint matrix, okay? A1, A2, A3. Now my entire execution can be seen as a sequence of blocks I1, I2, I3. And now my constraint matrix is going to look like AI1, AI2, AI3, because I'm going to put these exactly in those places because I'm executing this block after the other. In the proof system, I'm going to get alpha as per this matrix. Now, the verifier does not have this matrix because it doesn't know the sequence of execution. Okay? I can't pre-process this directly because, again, I don't know. This I1, I2, I3 can be input dependent. Right? It depends on my input, like how many times I have to do a for loop. But there is a way where I'm going to push the complexity a little bit to the second proof. I'm going to prove that for the pre-processing step, I'm going to sparse commit each of these primitive blocks. And then in the second proof, I'm going to prove that there exists a sequence for which this alpha can be computed as a combination of the individual alpha i's. Okay? This is not yet zero knowledge. You have to do some work. But this essentially will, I am pushing some complexity, but that is really not too much. I can tell you more about the second proof. But really, the idea is that this is more like if you've seen lookups. Lookups is for memory and data. This is really, I'm doing lookups for computations. Like I am, these blocks, I'm just imagining they are, like at every point of time, I'm looking up a block. And what I'm checking is this MAC. For that you instantiated it with the right matrix. And that's it. Anyway, so this is how we can reduce the mux overhead really to a bare minimum. This is our roadmap. I'm going to conclude by saying that we have built this platform. Our goal is really to incorporate as many languages. We hope to even get like Onyx for machine learning languages. Also, CIRCOM, Cairo, NOIR, because there's been a lot of development of circuits, highly optimized circuits in this. We are almost done with CIRCOM. And once we do CIRCOM, we're going to get a whole bunch of circuits that you can just inherit via an API call in our platform. You don't have to worry about how to do a BLS verification or a ECDSA on some prime. All of this, there's been so much work done in the blockchain space to build really optimized circuits in CIRCOM. The other thing we want to keep that it should run everywhere. We don't want to switch to, hey, I want a high-performance device. So we want to still keep ourselves hey, we want it on a memory constrained device. And with that, thank you.
I think I missed the yes precompile, no precompile answer.
Yeah, the answer is that you need we are doing precompiles, but in a generic way. That's the answer.
So you said code's going to be available soon. You're implementing the second prover at the end to do
yes.
that. So are you doing that with the second prover being Ligero or with something else?
Ligero.
Okay. So it's Ligero calling Ligero. Yeah. Okay.
Yeah. Yes.
So what about so is there a way to make this like an incremental prover in the sense that if I have 1,000 transactions to verify, can I start building the proof as the transactions are coming in? Or because of the 3 passes, I have to wait until all 1,000 transactions that are in, and only then I can start building the proof? So
I want to say yes and no. Yes, I do have to do 3 passes, but no in the sense that that we are doing it, this encoding can be done in parallel. So really, I could have designated rows for each transactions that they could do in parallel. And when I come for these constraints, if they are still there, I could use them, right? So I would lose memory efficiency because I'm employing a bunch of nodes to do this. But there is a way to do this in parallel if you give memory. I don't need to wait because I have this. I can shard the witness in the matrix in a nice way per transaction.
So you're saying you could. This actually is an incremental prover. It could actually start building a proof before the entire statement is ready.
It can.
I'm saying yeah. The transactions are dependent.
But then there's connection with Merkle tree, so no, then it has to be sequential. I see, right? If you're going to use Merkle roots for the accounts, etc., then there is yes.
So it's not quite an incremental prover.
Yeah.
Okay. It sounds like actually an interesting open direction, maybe.
that you can in parallel.
Not in parallel. So what we'd like to do is we'd like to basically accumulate transactions, let's say at one transaction, just to be silly, one transaction every minute. But as soon as the last transaction comes in, I only prove the last transaction, and then the proof of the entire thing is ready.
Yeah, that'd be interesting. As I mentioned to you before, I do think there is a way to make it with folding, like the same way as ARC.
Gotcha.
Then we could do that.
Okay, that makes sense. Thanks.
Questions?
Okay, thank you so much for this. Almost.
Yeah, sorry. So about the memory efficiency, you explicitly ruled it out, and I think it's good to not consider like recursive proofs, but still if you can comment like in the comparison of memory efficiency of recursive proofs versus what you get.
I think I won't be able to say anything more deeper than saying that recursive composition is a heavy step, right? So you're going to you can make it memory efficiency by sharding and like proving the starks, but there is really my understanding is that recursive composition is heavy. Like proving the recursive composition is heavy. So two things if you were going to do it on a browser. One is that you will have to do these sequentially, which actually these modern ZKVMs, they like use any number of nodes that do it in parallel, and even the recursive composition. If you wanted to get memory efficiency to run on the browser, you don't have that. Our implementation actually is a single-threaded browser implementation. So you will have to do it sequentially and then do the recursive composition. But really an implementation only would tell how efficient or inefficient it will be.
Thank you for the talk. I'm curious how the approach that you described on the last couple slides is different comparing to what ZKVMs or like RISC-0 or SP1 does like they are producing a verification key, trying to capture the topology of the internal memory structures of the program produced. And you are just telling that, okay, let's take some intermediate representation, find the independent blocks, and put this topology into these metrics.
I mean, I think maybe I can't say too much because we haven't finished implementing our thing, but if I had to guess, the advantage that Succinct Labs and like RISC-0 have is probably the pre-processing part is easier. It's more uniform. I have like a CPU circuit, so it could be smaller, like the key part of it. And for us, I'll have to commit to each block of it, and that could be big. And the complexity of the second proof could be bigger. But where we will gain is in that our polynomial commitment size, like the number of wire values, would be significantly smaller than theirs. So there could be a trade-off, and we need to sort of implement to figure this out.
Yeah, you are saving on lookups
Yes.
between the circuits. This I understand, but nevertheless, like without passing the verification, like it is possible to reduce the complexity of the circuit interaction in the VM model and trying to use VK more, like offloading the complexity into VK verification part.
So yeah, maybe we can take it offline, but maybe there's one remark I want to make is that we have to do a lot more effort in the second proof to make it ZK, but if you didn't want ZK, there is actually a solution where I give you the sequence I1, I2, I3. I don't even do pre-processing. The verifier just needs to compute this once locally, and then it can compute the alpha and check on its own. So if you're okay with the snark, then there's an easier solution to do that without pre-processing.
Okay. Thank you for a very successful demo and a very inspiring and interesting presentation.
Thanks.
So this concludes our second day. I hope you enjoyed this succession of conversations and deep dives. We have more to come tomorrow, a lot of talks about formal verification and more talks about ZKVMs, some talks about standardization. So keep some of that energy also for tomorrow. See you tomorrow.